So now let's now let's move to our lecture. Today we're gonna learn in the last lecture we learned on-policy method with approximation. In this lecture we're gonna learn off-policy method with approximation and the eligibility traces. Our focus actually in this lecture will be the eligibility traces. In this off-policy method with approximation, I just pick some algorithm that may be useful for you. Okay. So the first one is that we're gonna recall the estimated version of SGD. As you remember, so when we design the parameterize the update process, we design this estimated version of SGD. So we put this the UT is the target, then we minus the current estimate to get some error or updates for the estimate, and times the gradient of this state with some time step with the current weight, then we can update the next one, right? So this is the previous way we learned how we design this estimated version of SGD. So now today we're gonna use similarly today we're gonna use this estimate process or update process to design both prediction and control method based on the off-policy. So previously, when we learned the off-policy prediction, we learned the important sampling in the off-policy MC prediction, if you remember, if you recall, right? Specifically, we define this important sampling ratio based on the target policy pi and behavior policy b. So if you recall, you remember how we calculate this. So actually, I showed you the actual calculation process, each step for the algorithm. So you will have a lot of components of this row, and you will have products of multiple this ratio together for each time step. And also we learned that the incremental implementation, right? How we can design an algorithm that is kind of incrementally updates this important sampling ratio for the state value of the action value. So now actually we can reuse this important IS ratio to update the weight. So actually the method is straightforward. We just put this ratio in front of this the action value updates, okay? In front of the state value update. So since it's off policy, so we just put here row T to rescale the current update. Now the delta T, so there since we have two problem settings, either episodic and discounted or continuing and undiscounted. So you will have two this delta T setting. So delta T, if it's episodic and discounted, we will just have, since this is TD0, and means the one-step TD. Okay, this is one-step TD. We just use the current step to update the previous step. Current step update previous step. So this update process should be familiar with you because we have been using it. We have been seeing this many times. The next step reward we receive, and with discounted current state values with the update and minus the the previous state, the estimated state, and we do this is kind of a TD error put to here, and times the gradient with this IS ratio, and then we can update. With this way, we can update the weights. So, through all those processes, each episode, then it generates the trajectory and update step by step. If it's continuing and this undiscounted problem setting, so we use the differential return, right? The current step reward minus the average reward average reward and plus the current estimate of the seed value without discount, the gamma, okay, without discount factor, minus the previous steps estimate state value. So this is observed the PD error. Actually, the method is straightforward. There's not much. It's kind of move the previous what we learned knowledge into this new setting. Now we kind of move to the control method. Previously was the prediction, update the state values. Now we're gonna update the action values. For control problems, we can extend the semi-gradient expected SARSA to a off-policy version without RS. So if you recall the semi-gradient expected SARSA, so I mean, if you don't, if you just remember the expected SARSA, what is the expected SARSA? When we do the update, we choose the action based on the best action, the value, instead of based on the current policy, right? We call it expected SARSA. Expected SARSA is that we're gonna check every possibility of the action we have, then we put them up into the updates. So similarly, we're gonna use this expected SARSA here. As you can see here, we put all the possible actions from the policy. So even though we are using the policy, but the action, choosing the action is from the expected action, not from a particular action from the policy. Okay, so it's a statistics average of the action. The pi, if you remember, the pi itself is the probability of different action. For a particular action, it has probability. So we just do the expected average, then times the Q, the current action value, Q, with discounted gamma and plus the reward in this action. Then we minus the previous action value, which serves the error. Then we put into the delta t. Okay. If we have this continuing and undiscounted problem set, so you will see similarly actually. So this expected SARSA term is that we're gonna check all the possible actions from the policy pi instead of choosing just one particular action. So with this update, there will be no gamma for discounting, and we have this differential return. Okay. So actually, for this one-step semi-gradient control method, it's still some like ongoing research, because when people apply this one-step semi-gradient control method, sometimes it's just not cannot give good result. So that's why I put this note. It is less clear that whether this is the appropriate settings for control problem, and it is still under research. Okay, people still investigating why this approach does not give quite good performance, or sometimes it's not stable. Now we move to on top of that, we move to multi-step semi-gradient control method. Previously is one step. Now we move to multi-step, or you can consider n-step. Similarly, we extend the n-step semi-gradient SARSA to the off-policy version by the importance sampling ratio. So in this case, the update process becomes complicated. So we're gonna use the multiple components of this row, right? So each one will have the ratio, and we accumulate, we make them product together, times is the return. Okay, the return itself will be the rewards, accumulated reward, right? Minus this estimated action value times the gradient with the time step learning rate. So then for the different problem setting, we have episodic discounted problem setting. This as I mentioned, this gt to t plus n will have this shape. If you remember this n step salsa, it will not be strange for you. It just kind of a multiple n step return with discounted. Okay, and the last item will be the current state, the action value discounted. For the continuing and undiscounted setting, so you just multiple differential return, okay? Differential return. So it's like the current reward minus the average reward. Current reward minus average reward until the n step. Then plus the current action value. There will be no discount here, okay? This is two setting. Then the IS ratios will be the same, so we can just follow the previous setting to calculate the IS ratio. Okay. Then there's a special treatment on the end of episode if we use this episodic and discounted, because so when we design the algorithm, so if you remember when we design the n-step, either n-step like a SAR or n-step TD0, we always need to consider 2 points, either how many steps we need to wait and the end of the episode, how we deal with, because there will be no enough steps for calculating the n, right? The n-step reward, n-step return. So in that case, if we reach to the terminal state, then the absent the IS ratio will be 1. The rho k will be 1. At the same time, the GT will be just equals the current the MC, the total GT until the terminal state, right? The GT. So if t plus n larger or equal to the t, is to deal with the terminal states. Then for the waiting state, we already considered, right? So now we have another extension. We can, so if you recall the tree backup algorithm, I don't know if you remember it or not. So it's like, so the calculation process is a little bit complicated, but the thing is we have those backup diagram. So each action, then we have a like tree-like action selection. Then we will select the action that does not contribute to the next state as the update for the previous state, and select the action that will contribute to the next state as the return. Okay, so this is the calculation process. If you don't remember, you can review, go back to the previous lecture. I don't remember which week we had this. You can check those slides. You will tree backup algorithm. You will see how it works. Okay, the actual updates is here. We use the n step minus this q. So this n step return is calculated in this way, a little bit complicated. So you can check detail of this based on what we learned in the tree backup algorithm before. Then this delta t is the same to the expected salsa. So this delta, which is delta k here, okay, is similar to you will do the sum operation, sum all the possible action except the action that will be chosen for the next state. Okay, the next states will be the action chosen from the next state will be used for the times the current all the possible action. Okay, this is how you can calculate this n-step tree backup algorithm with the off-policy version without IS. Okay, this is the summary of these off-policy approaches with approximation. What we learned. So we can have the off-policy semi-gradient TD0 with projection by the RS importance sampling. So we just put the rho t impulse sampling ratio here. And for different problem settings, there will be different delta t, the error, right? Correction. Then if it's for control problem, we use the semi-gradient expected salsa without RS, because it's expected salsa means that we're going to consider all the possibilities. The salsa is reflected here. The sum operation of the policy pi. Similarly here, sum operation of policy pi. Then eventually we move to the multi-step semi-gradient control method with the IS ratio. Okay. So I didn't put the other information here. But this is since actually some contents in this section, in this scope, in this domain, are still ongoing research, and so I just select some of the kind of approaches that are familiar to us, and some other approaches you may check the related research papers or textbooks. You may see more information. And actually, yeah, even recent several years, there are some new results that have been published related to this off-policy semi-gradient method, either control or prediction. So yeah, before we move to the next topic, let's take a look at this. Let's take some to see how some real-world application of this learning to walk with deep reinforcement learning. Okay, so the goal of this, so this team, they developed this let's say this machine. Okay, so they have the 4 feet here, and I don't know how they designed their motor to move these feet. And so for this machine itself, it has no knowledge how to walk. It just can stand there statically. So then they're gonna train this machine to walk, how to walk. With actually, this machine itself does not have any knowledge about this, how to walk, how to move forward. So you will see how it works, how they move. So while watching this video clip, you will consider what is the action space for this machine. So at this 0 minutes, okay, at the beginning, this machine has no knowledge about moving, how to move. It just kind of trying. So I guess each feet has a motor to rotate this feet. So after 80 minutes, it kind of have some ability to move. But actually, if you observe, sometimes it just fall down and need to human intervene. Yeah, then go down. After almost an hour training, it kind of learned how to move, how to walk forward, right? Now the computer inside of this machine, then it can kind of generate policy for the 4 motors, how to rotate the motor and move forward. After 90 minutes, actually this machine almost learned. More than 100 minutes, so this machine already learned how to walk forward, right? So after learning the policy, they also tested with different factors, give some the forces from outside to test. You see this actually from the advanced version of this from the dynamics, the Boston dynamics, right? They also train this. They have a more robust behavior. So you just kick the machine, it will rebalance again, and walk again. So it's tried to move different terrains, that is work on a slope. So eventually their policy is moved to on the stairs. So it's, yeah, kind of the policy is kind of getting better. Hit some blocks, not seeing it changing. Okay. So this is how we can train some like robots in the real world with the deep reinforcement learning. So I will ask some questions. What kind of action space it has for this mission? So as I mentioned, each bit has a motto, right? For that motto, what is the action space? Depends on the type of motto it uses. So it may have some rotating degree. So for each degree, they may rotate, right? Then for the four mottos, they can group some rotating like action space, like 1 degree. So each motto of 1 degree rotates. So you may have a very large action space. How about since they are using the deep reinforcement learning, means that they use the neural network to train their the policy, the action. Then what will be their state space? Any idea? Anyone? Because they are using deep reinforcement. In what kind of circumstances we're gonna use deep reinforcement instead of the just general reinforcement? Maybe this robot has the sensor of camera just shooting around, or it has some sensor, ultrasound sensor to detect the distance toward front, like front wall. Then with that sensor information, and if we have multiple sensor information together, then we build the state space with the input of the neural network as the input, as a feature, right? Multiple sensor information into the feature. Then we design multiple layers of neural networks. Then we link to the policy, the action space. Through this process, then we iterate, generate, update the weights. So this is kind of a application in the real world, how to use the reinforcement learning. Okay. So let's take a 15-minute break, 15 to 20 minutes break. 1:30, let's come back. Okay. Okay, so now we are going to move to a new topic, which is called eligibility traces. Okay, eligibility traces. So, okay, so let's take a look at our reinforcement learning framework. So far we have been learning, for this agent, it has the policy pi, A under S, and state value function. Now we are moving to this parameterized value function. For action value function, it's also parameterized with W. Now we are going to introduce two new parameters, lambda and z, for these eligibility traces, ET. Okay, these two parameters are from these eligibility traces. So we're gonna see how we can use lambda and z to improve the performance in those approach we learned before. A little bit introduction about this ET. Previously, we learned this TD0. So it's just one step TD. So actually, at the time, I didn't mention why use the TD0, not TD1. If you consider it one step TD, why we use TD0? Actually, this number of 0 indicates the eligibility traces. So means that actually the 0 is a lambda. It's TD lambda to represent ET mechanism. Okay. So we call this lambda is trace decay parameter, and it belongs to 0 to 1. Okay, it should between 0 to 1. And so this ET traces unify and generalize TD and MC methods. So previously, if you remember the TD, one-step TD or n-step TD, so the one-step TD is just that we move to a new state and we update previous state. Move to a new state, update previous state. MC is that we need to move to, when we move to the terminal state of the current episode, then we update all the states one by one, right? So ET kind of unify and generalize both methods, both kind of methods. Particularly if lambda equals 1 means that MC method, TD1 means that we will only consider at the end of episode, consider all the return from the ending point. If lambda equals 0 means that it's the one-step TD method. So we just move one step further and the update previous state. So in between, actually, they are kind of intermediate method. Most of the time, it's better than both either method. And from another point of view, if you look at ET, so especially ET is a short-term memory vector. ZT, here we use ZT to define a new vector that represents the short-term memory that belongs to a d-dimensional real number. So actually, this ET will have the same dimension with the weight vector, or here we call it long-term weight vector. So previously we used WT, right? To represent, WT is the weight we're gonna use for the estimate the state value or action value. So we call this WT is the long-term weight vector, and ZT is short-term memory vector. And this lambda actually adjusts the falling rate of trace in ZT. Okay? Falling trace in ZT. And we're gonna take a look at detail about how the ZT and lambda work in those new setting. It's a new problem. So before we jump into those approaches, we first take a look at some advantages of this ET, of a learn method. So far, we learned this MC or TD method update, right? So it's like it needs to rely on future reward. Like we are standing here, like we need to move to further to the future, and we are currently here and move and update the previous state. So the previous state need to be waiting for the future state reached. So we call it forward view, because when we update, we need to move to the current state, then we can update the previous state. So from implementation point of view, it's complex, because among those multiple steps, we need to actually save those data, right? So if you consider for grid word or some random walk, so kind of the setting is simple, the states information is simple. So actually we don't need to save a lot of data, but for real world, for each state and for the road reward action, we need to save a lot of data, like unstep data, so which is not very good to implement. So but ET mechanism can achieve nearly the same update, looking backward to recent visited states. Then we call it a backward review, means that we don't need to save those data. We just stand at the current state, and we are looking backward, then check those history data and update the current state. And other advantage are strength is that we just use a single trace vector. Then we don't need to rely on the last feature vectors. And we can learn it continually and uniformly in time, and will not be delayed. Because previously, if you remember, like n-step TD, you always need to wait like n-step later. Then we can update the state we want to update. For the MC, You need to wait until the end of the episode. And also, the learning will occur and affect behavior immediately. Is similar to the previous one. So once we can update the state, then the policy will be updated immediately instead of wait until like a step later, then we can update the policy. So there are several strong points here. So before we start in learning this ET mechanism, we first move back, take a look at so far the principle what we learned so far. If you remember the n-step return we defined, it's like we used it in the n-step TD or n-step startup. We define this n-step return. So it will just accumulate the n-step rewards, right? 1, 2 until n-step, and with the current estimated state value. So we define it as a gt to t plus n, the n-step return. So actually we learned is that the reason it can work is that because it has the error reduction property. Okay, this is the basic principle. If it doesn't follow this error reduction property, it cannot converge, cannot kind of gradually reach to the optimal state. So this is the basic principle. Whenever you design something, if you follow this basic principle, it eventually will converge, will reach to the close to the optimal state values. So if we follow this basic principle, whenever, as long as there's an error reduction, then it should work, right? So now a valid update can also be done by, here we call it average of n-step returns for different n. For example, so maybe when you look at this description, a little bit abstractive, average of n-step returns. So it means that, for example, here, we can select 2-step and 4-step return and do the average. So each component contributes 50% of the return, the update in this case. So that's why we call it average of n-step return. As long as the percentage sum to 1, then it should work. So here, so this is what we call if we follow the basic principle, as long as it has error reduction property, it should work. So if you look at here, the average of n-step return, obviously it follows. It just kind of select different components of the n-step return, right? We select the 2-step return plus 4-step return. Then each one of them will have a 50% contribution to this update. But still, they have this error reduction property. So, yeah, then the design here is as long as the weights on the component return are positive and sum to 1. Sum to 1 means an average, right? We have 2 components, then we have 1/2, 1/2. So this new settings bring us a new range of algorithms. So it means that actually we can design different kind of algorithm as long as we can combine any future return. For example, if we can combine 1-step TD and MC together in this way. Okay. 50% of 1-step TD, 50% of the end of the total return, the whole trajectory return, right? We can do this. Each one of them will contribute 50%. This is by following this basic principle, or we can generalize it. We can just combine any future return together as long as they are positive and the sum to be 1. This is the idea behind the eligibility traces. So now if we have this idea, we have this thinking, now we can redefine the n-step TD by so-called lambda return. Okay, lambda return. So this lambda return is, we use this lambda to represent the ratio, the percentage. Previously we used here 1/2, 1/2. The lambda is representing the ratio. So for this average simple components update, it's like the previous one, combining multiple future returns. So we call it compound update. Okay. So previously we say here, combining any future returns. If we design a particular one, for example, here we use the one-step TD and MC, we call it compound update. So its computing depends on the longest component. In this case, the computing depends on the MC method. It's the longest, right, for this particular episode with the GT. So in that case, we may need to limit the length. So then how to select the step? In general, so we can generalize it, this n-step TD based on the new setting. We call it TD lambda with this lambda return. So in specific, we use the decay function to rescale the n-step return. So a little bit, if you look at here, decay function. In specific, we use 1 minus lambda times the sum of lambda to the power n minus 1. Then the n is from 1 to infinite, then times the gt. So you remember the gt to t plus n. So it's another sum for multiple rewards, right? So we use this coefficient to rescale the different components inside of this n-step return. So if you look at, I showed this, if we look at this function, this decay function, 1 minus lambda times lambda to the power x. So you will see this decay. So the y, the result of y will be decreasing. Then if you do the integral, the area of this below this shape will be equal to 1. Okay, the sum will be equal to 1. So this guarantees that the sum will be 1. So the component of each component will have the total contribution will be 1. So each weight proportional to the lambda to the power n minus 1. Okay, lambda belongs to 0 to 1. And normalized by a factor of 1 minus lambda to ensure the sum to be 1. So as I mentioned, if we consider the function of this decay function, if you do the integration, it will be equal to 1. But from this discrete point of view, why this? We can ensure that this to be 1. Why? Anyone? If you consider this n steps reach to the infinite, this is from 1 to infinite. So actually we can calculate this part, right? So 1 to infinite with this power lambda to the power n plus 1, if you do the calculation, it will be equals to the 1 divided by 1 minus lambda. Actually, in the midterm exam, there's one problem. We used this conclusion. Also in the textbook previously, you will check, you will see actually this infinite summation will equals to 1 over 1 minus lambda. So if you times them together, actually it will just be equal to 1. Okay. So, yeah, any questions? Okay, we continue. If we separate the state after the termination, the lambda return becomes, so we just assume that because this is infinite, then we separate we consider like the sum of terminations points, then we put to here, then we just get the termination point and plus the remaining point. Now, we use this backup diagram to check what is going on there. Okay, TD lambda. So this is one step TD, two step TD, three step until the terminal state. So if lambda equals 0, if you go back to the previous one, if lambda equals 0, then we just equals 1, then this is 0, right? So actually it just equals one step TD or TD 0. If lambda equals 1, so it will just equals the MC, because if you look at the separated version, so the previous part will be 0, then only the separated terminated part will be remain. So if we from here, if we expand the previous setting, if you look at here, when n equals 1, the coefficient will be equals 1 minus lambda. Then the gt to t plus 1 will be equals t plus 1 plus gamma v, right? So this is the first component. The second component is 1 minus lambda times lambda. The previous lambda is to the power 0, is to the power 1. Then the gt to t plus 2 will be equals this shape. So we have a two-step return, right? Then n equals 3. Similarly, the lambda will have to the power 2, which is n minus 1, right? Then this is a three-step return. So if you continue to the terminal state, you will see the coefficient become this shape, and times this is the state before the terminal state, right? T minus 1, then it will equals to this shape. So the T minus 1 step return. If we reach to the terminal state, it will have this shape. Then the lambda will be T minus 1 to lambda to the power T minus 1. Then this GT to T, the return will just equals to the total return, right? Because the terminal state will be equal to 0, the total return of all the trajectory, all the state in this trajectory. If you expanded it. So just let's take a look at here. If we look at we combine this decay function with each component, you will see that what is happening here. Each component will be rescared by this decay function. The height is weighting is 1 minus lambda. So the first component, one step TD, one step return is here, two step return is here, three step is here, then decay until the terminal t. The remaining I just consider as the lambda t minus capital T minus t minus 1. Okay. So for this lambda return, if you just look at this shape, actually it kind of simple. If you expanded it, you will see it kind of very complicated internal structure. So I put it into the appendix. You will see how it looks like. So as I mentioned, we use the GT lambda to represent this lambda return. Okay, equals this shape. If we expanded this return, you will see what is going on here. So this one-step return is rescaled by this weight. It's coefficient. Two-step return rescaled by this ratio. And three-step. Eventually to the terminal state and plus the state after the terminal. So this is if you expand the internal mechanism or calculation process of this lambda return. Okay, actually this t to t plus n itself inside has the sum operation. Actually, we have the two sum operation here, and this is the coefficient to this each component of this sum. Okay. Any questions? So it's kind of a little bit complicated compared to the previous one. So if you look at here, if you design some particular lambda and with some n, actually we are going to use multiple components of n, like a particular n, to calculate the return instead of using some a range of reward as a return, right? So this is so-called the lambda return. It is one of the components, one of the factor in the eligibility traces lambda return. And so we will look at how we can use this lambda return to design the algorithm. So if we have this setting, this new defined lambda return, we can use this return as the estimate, okay, to update the weight vector. So with this, we just use this gt lambda minus the current state, and with the gradient, update the current weight. Then we can the previous weight, and we can update the current weight, right? So if you look at here, we can compare the, since also the name, we use the offline lambda return, means that actually we cannot update the state in real time. We need to wait until the end of the episode. We can update all the weights. So means that actually this, when we try to update this WT plus 1, we cannot update one step by step. Actually, we update at the end of the episode, and then we, from the beginning step, we update one by one. Because the calculation GT lambda requires that. Okay. Okay. I forgot one implication here. So let me ask one question. So here is the comparison, the performance comparison between n-step TD method and offline lambda return algorithm. What we just look at this update process. If you just compare these two graphs, so this is the previous what we learned, right? The alpha is the step size, and n is the step, multiple step. Which step is the best? The parameter we want to use. Actually, we realize that when alpha equals some number here and n equals 4, then we got the best performance somewhere here. So this is what we learned previously. Now, if we use this lambda as a parameter, we vary this lambda. And actually, when you compare it, except those best performance points around somewhere here, then the alpha will have a similar value somewhere here. So if you compare the performance, the best performance is good. But actually, if you compare other alpha, the performance from other area, if one alpha moves to the shift to the right or left, actually this performance is worse, is better than this one, right? Because so the lower of this the error means that the error is small. Okay, if you look at here, this is the rule mean square error. Okay, over the first 10 episodes. So if this shape is lower here, means that actually the overall the error is smaller than that one. Actually, if you look at compare to that shape, the overall performance, each kind of component is better than the unstepped GT. So this one, this shape is also somewhere here. Okay, so means that actually the learning speed of this offline lambda return is faster than unstepped GT, because those errors quickly reach to the optimum thing. And then one question here is that it might be a stupid question, might be a confusing question. What is the n in this offline lambda return algorithm? Here, the left-hand side. What is the n? Because here, when you see when we compare this, we vary n. In this case, we just vary lambda. What is n here? Anyone? So you have any thinking, you can just say it. Yeah. Sorry? Like, it's nine. Oh, yeah. 19 states are random walk. 19 states. Not really, because okay, actually, the number of n here is unknown. It's a random number. Depends on, because this is 19 states random walk. Actually, it depends on this n. When we use the GT lambda, it will use all the states of an episode. So the size of the episode is random. Depends on the setting, right? Because this 19 state random walk, as I mentioned in the beginning of this lecture, each episode will have a random time step, the n. So because we are using offline lambda return, actually the n is random, depends on, your simulation, the random number. You can either jump left or right until it jumps to the terminal state. It can 100, can be 200, can be 300. So in this case, it's a random, okay? N is random. There's no fixed n here. But actually, all these shapes will utilize all those random n to calculate the performance. Okay, that is one of the key message implication from these two comparisons. Okay, the n in this graph is random because we gonna use all the n to calculate this GT lambda, right? GT lambda, all the n's. But the n, when we generate the n, is based on each episode. The n depends on each episode. The n will be random, right? So it will be the random number from the beginning state to the end of the state, end of the terminal state. So this the size of the state, the time step is random. Then the n will be random. So it will just count every step of this random n, right? Okay, so this is one indication from this graph. So as you can see here, as I mentioned that this performance comparison shows the first merit or advantage, or the a strong point of the lambda return, because if you look at all those performance lines, overall the performance, the when you're running the simulation program, the general performance are better than unstepped TD method, right? Because this shape is lower than those shapes, lower on the different settings. Okay, but actually, now we move to the next topic. But actually, when we look at this algorithm, this offline lambda return algorithm, when we say offline means that we can do this update only at the end of episode. So we're gonna rerun. So it's when the episode is end, then we run this from the beginning, W0, W1, W2, W3, W5 until the terminal state end, right? So we need to update. So we call it offline. So its advantage of this algorithm is that it's like the MC method. We can only update at the end of the terminal state. Okay. But so that's why I move in we will look at this algorithm again later. So for now, we move to another aspect of the eligibility trace, which is the vector ZT. Now we can use the ET lambda and the ZT to design the TD lambda. So a new design of this algorithm. Previously, this is offline. Now we are moving to the TD lambda. It's a different version of this offline lambda return algorithm. Okay. So now we introduce this ET vector. We use ZT to represent with the same dimension as the weight vector WT. So they have the same dimension. So how we define in specific, how we define it, you see this is the first time you see it. Okay. Its initial value is 0. So we use Z minus 1 subscript to represent initial value is 0. Then we update this ZT with gamma and lambda. Lambda is the one we can define with this ZT. Initially is 0. Plus this gradient of this state value. If it's linear, it just equals the feature vector. The summation of the feature, right? Just equals the feature value. So now these two parts add together. So this is vector. Actually, they will be added to every component of this vector and update this ZT. So this is initial and this is the current. Okay. This is what we define the ET eligibility trace vector, ZT here. Then we can look at several features of this ZT. ZT is increased by gradient and faded away by the coefficient gamma and lambda. As we just described what it is, right? Faded away. So since gamma and lambda both coefficients are the numbers between 0 to 1, right? So obviously the ZT minus 1 will be kind of reduced some ratio between 0 to 1. And it also plus the gradient. Gradient would be calculated. So actually it brings us the problem. What is the gradient? What is the gradient? Gradient defines whether this update is positive or negative, right? It's defined if it's positive, it moves to the right. So if it's positive, it will move to the right-hand side. If negative, it will down moving. Okay. So this is the meaning of the gradient. So actually, we add this gradient to these components. So it means that we're gonna track the gradient, the contribution of this particular gradient, whether it's positive or negative, as I mentioned here at the end of it. The ET tracks the components of weight vector that have contributed positive or negative. But here, when I say positive or negative, it doesn't mean the good or bad. Positive means that the increasing, negative means the decreasing, right? Sometimes it depends on the problem. Sometimes it's good, sometimes it's bad. Then here, WT is the long-term memory, updating over the lifetime. So as I mentioned, we call it long-term memory because with WT, we can update the state values or action values. So it will be existing through the whole training process. The ZT is the short-term memory, typically lasting just within the episode. So for this particular episode, we use this ZT to track the contribution of each step, each return, each step, the gradient contribution, right? Then ZT affects WT. WT determines the estimated value. So later on, we will see how the ZT affects WT. Then if you look at here, this ZT is just the accumulation of the gradient with some rescared number. So there's some ratio, small ratio. Then another name for this trace, we call it accumulating trace. Okay, ZT is another name. We're going to look at other types of the traces later. This name is called accumulating trace. Now, if we use this ZT along with the TD error, this is the TD error, what we defined before. Together, the delta T is here, okay, which is TD error. If you look at here, it's just one step TD, right? Yeah, one step TD error. Then put to here. So this is to here and ZT times with alpha is the learning rate time step is WT. We define this new weight vector update process. So this is the basic eligibility trace process, update process. Then the good point is that with this process, update weight vector every step. So actually, this is kind of online algorithm. For each step, we can update the weight. Each step update the weight and faster. Then computation distribution equally. So if previously, in the previous offline algorithm, when we need to do the update at the end of the episode. So it's like all the computation will be put on at the end of the episode, right? So during the episode, during the time step, there's no computation. So yeah, the computation distributed equally. That means that actually we have a faster update. Then can be applied to the continuing problem further. So if we consider continuing problem settings, actually there's no issue for this setting. It can just continue running, okay? Because it's the step-by-step base, not rely on the whole information in the episode. Okay, so this lambda, yeah, this gradient here. Okay, so later on, we may look at an example for this setting. So we just design this TD lambda with the eligibility trace. We used both lambda and ZT for this update. Okay. As you can see here, when we update this TD error, when we use the TD error, we use RT plus 1 times gamma V hat ST plus 1. So this is the current state and WT. Then with this delta T then times ZT. ZT is the history, the gradient, right? The previous state. So actually means that actually we are in the current state. We are using the previous state to update the weights. So also just be remembering that what is the meaning of the gradient. If it's negative, it's decreasing. So the direction is downgrade, right? Moving to the downward. If it's positive, it's moving to the upward. So actually, in our case, negative slope is better because we're going to reduce the error. It should be negative. It's better. But sometimes positive may bring some, the faster the convergence speed. So now let's from the forward or backward view to see. So at the beginning of the lecture, I mentioned that we are moving from the forward view to the backward view. Previously, when we look at this, the problem when we design, for example, n-step TD, like let's say 3-step TD. So when we try to update state value, for example, I want to update this ST. Actually, we need to wait until we reach to this ST plus 3, right? Then we can update this state. So this is called the forward view. So among this process, we need to save all those data, the state information and reward information and action information. So if you consider the real world problem, so this kind of data, each state of data will be huge. And you need to save all those information. So from implementation point of view, actually it's not good. Now we are moving based on this ET traces. We are now staying at the current state. Then we use ET and delta T combined to get those history data to update my current state. Okay, so now we just need to save the one-step data. Just one-step data is enough. We just use one-step data is enough. We use the delta T times ZT, right? This is the major update here. So just in case you don't remember this ZT delta T, if you look back, the delta T is so this is the RT plus 1 is the current state we are at. So we use the current reward plus current state value minus the previous state value and put as the delta T here. And what is ZT? ZT is based on the previous state, the ZT value and plus the gradient, right? The the gradient, the value of the state value, which defines the moving direction, is it upward or downward. So actually now we just need to save the one-step data. It's already enough to update. Then we can just update step by step. We don't need to save all those intermediate data. So any questions? Yes, sure. Yeah. Yes. Yeah. Yeah. So actually, yeah. Actually here the N doesn't matter anymore because we just use the one-step information. Yeah, doesn't affect the update anymore. So the thing is the key message is here. We use the gradient to track the history data, whether it's positive or negative, to contribute the current state instead of using the future information. It's like the information that future provides to us. Okay, with this backward view, any other questions? So with this backward view, we can design this semi-gradient TD lambda algorithm to estimate the state value. So as you can see here, now we have this new parameter, trace decay rate lambda. It's between 0 to 1. With this z vector initialized by 0. So all the elements will be 0 in this z. And so the updating process is just the equations we learned in the previous slides, okay? The z and delta and w, the three equations. So you can see here, we look back to the contributions of the history, and earlier states are given less credit for the TD error. So if lambda equals 0, then this aggregate is just one step TD. So from the calculation point of view, actually it's not that difficult, right? So look for each episode, initialize it, look for each step of episode. Then, yeah, we can generate the update so that we calculate the gradient. And z initially is 0, and is the gamma and lambda that's predefined. Then we can just update the first one. Initial 0, actually initial z, after the first step, z just equals the gradient, right? The next step we will use a new gradient. So the delta, so update the delta is based on the current reward, the current state value. S prime is the current state, okay? You see here, we choose the action and take the action of the R and S prime. S prime is the current state, the minus the previous state value. With this delta and z, we put to here, and alpha is the step size. Then we update the weight. And we update the current state to put to the S as the next step, and will be the previous step, right? Previous state. Let's iterate. Then we can calculate update the weight. This is so-called semi-gradient TD lambda with the eligibility traces. So now we can compare the performance. If you look at the performance, similar to the previous one. Actually, if you look at here, the performance, I mean, the optimal performance is similar. So now we are comparing the performance from the offline lambda algorithm, what we just see before, okay? Actually, it shows very good improved performance overall. All the settings, all the high parameter settings. And for the TD lambda, we vary the lambda. If you look at here, actually except the optimal point are the similar, but other area actually are worse. For example, you look at here, lambda equals 0.8, lambda equals 0.8. So you see this line lower is better, but actually if you compare to here, this line is higher, which means it will move somewhere here. So when alpha moves to other area, other values, actually the performance is worse. So the error becomes larger. There is some gap here compared to this blue line. So actually this is the issue of TD lambda we are having, because TD lambda is so we will look at later what is the problem here, why we have this error, some like a downgraded performance. We can compare here, okay? Offline lambda is somewhere here. It's TD lambda is here. There is some gap. The performance cannot become worse. Similarly to others. But the optimal point is similar, okay? So now we move back to the forward view in the offline lambda return algorithm. It's this shape, right? Offline lambda return algorithm. So we used this lambda return, GT lambda, to update get the error and to update the state value, the weight factor. So since this is, as I mentioned, there's a limitation for this, right? So because we can only update at the end of episode, And for continuing case, it's never known. It's GT, this one. So we can only can only use this one at the end of episode because it will use all the n, right? Only when we reach to the end of the episode, the n is known to us, then we can generate the GT sequence, GT lambda sequence, right? Because n is a random number, we don't know until we reach to the end of the terminal. And if it's continuing case, we don't know n anymore because n it can just run forever. N is the infinite. So we will never get this GT lambda. So in practice, this is the kind of limited we use. So with this in mind, naturally we can just do some truncation operation to this GT lambda. So we don't need to. So we can limit it n, right? We can limit it n to some intermediate point instead of using all the n. Because if you consider the decay, the function, when the n becomes larger, the remaining, so those tailing components are very small, have very limited small effect on the overall return. So with this idea, we can just truncate the horizon to some later step. We use h to represent. Then we have this so-called truncated lambda return. We define it in this way. So previously, this t to t plus n. Now we just select the particular period, the time step. Then we stop there. We just use all those t to h. Then we just replace those previously the if n, so because we need to reach to the end of terminal, actually h was t. Now we just until the terminal, then we just select a particular number. But for the continuing case, there's no terminal state, so it's just some number here. So yeah. So the overall process, the component, the structure of this calculation, that this lambda return is similar. We cut off some remaining stuff. We just specify a particular h. Now, in this case, it's kind of we move back to the n step. Instead of using n step lambda return, now we kind of this n step, we use partial of this n number instead of using a full n step number, right? It's just we don't need to wait until the end of the episode, or we will never know the lambda return. So then the new design return is in this shape. We call it truncated TD lambda or TTD lambda. So actually the mechanism is similar. We just remove some part of the return. The backup diagram. So we just reach to a particular number n instead of using the whole episodes number. As I mentioned, the whole episodes n will be random. Actually, we don't know until we know, right? But this is the diagram. Now, so previously when we mentioned that the TTD lambda, so the truncated, actually when we design this, actually now we are dealing with this n, right, or h. So when the truncated, we use the h to represent, right? So actually it's affected by this n. So if the n is larger, then it becomes the offline, close to the offline algorithm. Then because we have more data, then we have a better update. If n is too small, then the good point is that we can make the update quicker, faster, right? Like several steps we can update. But now how we can balance both sides? We want to get both merits together. How we can do it? We can do it, but with a high computation cost. So the idea is that we can just go back and redo all the updates since the beginning of the current episode, from the beginning of the timestamp. So, but the thing is, there's a high computation because it means that previously when you do this offline lambda return, you update the state from the beginning one time, you just update. But if offline, you need to wait until the end of terminal states, right? Now, if you just choose some H intermediate, so you can just each step you update one. To the second step you update from the beginning again. You consider every step as a terminal state. You just update all the weights again and again and again. But the computation cost is high. Means that you're gonna work through all the trajectory again and again and again. So with this in mind, then at the time t with horizon h related to n, okay? We use WTH to denote the weight. So it's like now this stop a little bit. We add this superscript h to represent the intermediate step. So we use this. Here I use the horizon, the intermediate step, till n, right? So we use the WTH to denote the weight. The general form of update is in this way. So the update process, so we put the H as a superscript to represent this is the intermediate step instead of the whole step. Then we use the intermediate return, means the truncated return, right? It's the intermediate weight. So actually the update process is similar to the offline. It's just we use the intermediate step to update instead of update at the end of the state. So this kind of update process defines the online lambda return algorithm. So if you look at the detail, that's how it works. So it's, as I mentioned, H is the intermediate, the truncated. For example, actually there's some n, so we don't know. But intermediate, we can truncate the update process. If H equals 1, you just update one step. Then we can we just update the W11. So this is time step. This is the truncated n or H put here. So this is W0, the initial weight, then updated by this intermediate return. So this is general the update process, right? This is the first step. Then when H equals 2, if we truncate it to 2, we will update the weight from the beginning when the weight equals the time step equals 0. Even though we are in the truncated 2, so this superscript will be 2 because we are using the intermediate step 2. So actually this value is equals to W. If you consider time step W0, here is same to the W01 here. But from time step point of view, they are the same. So when we reach to this point, we're gonna redo from the beginning, update from the original initial weight vector. We got the first update. We use the first update the second update. So this W12 will be used in the second update and calculate W22. When H equals 3, now we can, similarly, we're gonna use the weight from the beginning, W0, to get the first weight. With the first weight, then there's two parts, then we update the second weight, W2, W3, similarly. So until some like n, we will redo this again and again. So that's why we call it's online. So each step we can update the weight. We get the latest weight, means that we get the better estimate of the state value. But each time we need to update from the beginning of the weight. So that's why we say this is online update, but with a high computation cost. Any questions? Okay. So now let's compare this. So previously you see that the TD lambda has the performance become worse, right? Generally. So now we use this online lambda return algorithm, the one we just saw it, and compare with the original this offline lambda return algorithm as a baseline, because it actually shows the best estimate for our case. So you see here, the performance almost similar now, because now we use this truncated online lambda return algorithm. Even though the computation cost is high, but actually we update real time, and the update information is kind of real time. So we got all the information from the episode, right, to update. That's why the performance is better now. So this is how we improved from the previous TD lambda. TD lambda is just native implementation of the eligibility trace. So now, actually, since here, as we mentioned here, we have a lot of this computation burden here. Each step, each intermediate step, we need to re-update all the process, right? As I mentioned. So can we find a way, a better way, that by gaining both the merits, either we have this real-time update and accurate, better updates, and also less computation cost. Actually, there is. It just actually this result is just published like 7 years ago in 2000, yeah, 7 years ago. Yeah. So they just published this result. So but actually how they derived the result actually very quite long. We don't go to detail, we just see the result, okay, like their conclusion. So as I mentioned, the current presented online lambda return algorithm is very complex. So can we do it better? So if you look at the weight, we are updating the weight. So each h equals 1, we got and this is the initial state. So when h equals 1, we update the weight from the beginning to W1, W0, W1. When h equals 2, we update again from the beginning. Update. So if you observe this one, actually eventually the useful weight only is the diagonal weight is useful to us. Or other intermediate weight is just for the calculating the diagonal weight, the final weight. Right? If we can find a way, just calculate the diagonal weight based on the previous weight, then all the computation during the intermediate, we don't need to do those computations, right? So this is the idea here. Means that we just need the diagonal weights. In the intermediate, those weight calculation, actually we don't need. But in the previous setting, we need all those because W2 is relying on W12, right? So how we can find? So actually, this is the result, the conclusion. How if for a particular case, if the state value function is a linear case, means that VSW equals W transpose times X. Yes. There's a linear case, only works for linear case. Actually, they find the way to do this calculation. They find a way to design this VT they call it Dutch tree. Okay. Actually the result is quite complicated. So this is the same what we see, but the gradient part becomes this way. And if you are interested, you can check their paper. It was published in 2016. Recent published paper. How they derived this result. Okay. Then in this way, also the online TD lambda update is how they derived this way. The update process is also different now. If you are interested, you can check this paper. I give the link here. Then in the appendix B, they gave like the detailed derivation process, and maybe has three pages, as I remember, how they derive this process. But anyway, so they find a way, efficient way to do this calculation. So kind of balance both the calculation computation cost and the speed and the accuracy, the performance, better update. But I need to remember that it's only for the linear case. If this value state function is not linear, for example, if designed by like a nonlinear case, so it cannot work in this way, because when they derive this solution, they need to use the linear function approaches. Okay, so then with their solution, we can design this true online TD lambda. And we don't go to the detail of this process, but I just mentioned several key points. So because their precondition is that it only works for the linear function of the state value. So here they directly use x to represent the state. Okay, x prime means the current state. Directly use x. So they don't use the, so this v minus v old, v minus v old. If you look at the previous update, so it's just the here, right? This is the v minus v old. So the previous state value and current state value, because this is the linear case. So actually, this is the state value. State value, current state value minus old state value, and times this. So from the calculation point of view, actually, it's not that difficult. Okay, this is the true online TD lambda. Control. Now we can move to the control area. So far, previously we just for the predict the state value. Now we move to the control area. But naturally, we just use the Sasser lambda. So the Sasser lambda, we use it. We merge the concept, the idea of ET with the Sarsa and the lambda. So previously we had this unstepped return, right? So it's the same. Now we can define this lambda return as this similar setting. So actually all other processes same, just we replace the state value with the Q value, action value. Okay, the update process is same. And then we call this method Sarsa lambda. Then update the TD error, ET vector, all are the same. And sometimes we can also use this so-called replacing traces for binary feature vector. Okay, so actually the beginning we had this left-hand side. This is called the accumulating trace. And in the previous setting, we had the Dutch trace. Now this is the third type of trace called replacing traces. If you look at here, if this binary means either 0 or 1, if the feature is 1, we just use 1. If feature is 0 otherwise, usually 0, we use the decayed or partially of this VIT minus 1, the previous ET vector. Okay. So this update TD error is same to the previous one, right? If you look at now we look at some example. What is exactly it looks like in the grid world? So previously, if you remember, we learned this like grid world. So our starting point is here. Then we want to move to this goal place. For example, we generate a trajectory, this trajectory. If it's one step TD, action value, one step Sarsa, okay? If it's one step Sarsa means that you remember the setting, right? So only when you reach the goal, we have a reward. during the movement, the reward is 0. Actually, there's no information whether our policy, our action is good or not, because there's no information. Only when you reach to the goal, you have the positive 1 reward. Then it kind of justify the whole trajectory. So if we use one-step SARSA, you have this trajectory, but you can only update the policy one step before the goal, which is here. Okay, this is one-step SARSA. What do we have? Now, if we extend the one-step SARSA to 10-step SARSA, means that before this the actual reward return we have, then we can trace back, update the policy 10 steps before. Okay. Yeah. So before the then before the 10 step, we don't have the information. Yeah. We cannot evaluate all those steps. Now we move to the SARSA lambda with lambda equals 0.9. What do we see is that since you remember the lambda return actually covers all the trajectory information component. But we use the decay coefficient to rescale that. For this policy, we use the first one, the largest one, the coefficient 1 minus lambda. The second one, 1 minus lambda times lambda, then continuously rescale. So we have a decay. So actually, all those policy will be updated through this trajectory. Okay, this is the indication. What do we have? So yeah, so the last one, this is for the mountain car. Since we are reaching the point, I just simply 1 point. As you can see here, SARSA lambda is much better than n-step SARSA, just in terms of optimal policy. So it can only reach to here, which is about 222, but SARSA lambda reach to the 180, the optimal policy. So it means that we use less time steps to reach the goal. Or in the mountain car problem, we learned that last week, lecture or 2 weeks ago. Okay, this is how SARSA lambda improved the overall performance. But this is a summary, so I don't go through detail. This is just what we learned. Okay, that's all. Thank you for your attention. And if you have any questions, so you can send me the messages. So next week we will have a quiz again, okay? For this content today. Thank you.